Hey everyone, it's Dr. C. This is the second part of the recording of Exam 3, the answer key. But before I get to that, very short pre-lecture. I just wanted to clue you in about the final exam. Okay? So the final exam is cumulative. That means it's going to cover the whole semester. I will provide a study guide that breaks it down into coverage. And the coverage is going to be pretty equal throughout the semester, but I will kind of clue you in, how many questions on thermodynamics will you have and what areas those will come from. How many questions on kinetics will you have and what items will those come, what areas will those come from. So I'll try to help you out there. There will also be, there will be both a study guide and a practice exam. Okay, so that should help you get ready. Okay, there will also be review sessions, and I'll let you know when those are in class on Thursday. I usually run a few review sessions for the final. Okay, now one important thing you can do to boost the final score for everybody. Okay. And I hate to do this to you because we just asked you to do the adaptive learning survey. But if you do the course survey, for your courses, you can evaluate all of your courses and your instructors. If our classes can get to 70% response, so 70% of the class responds to the survey, I will add 3% to your final exam score. Okay, so you don't have to send, you can send me a response telling me that you completed the survey. If you want to do that, that's okay. You don't have to complete the survey. You just have to trust that your classmates will get to 70%. And if the class as a whole gets to 70%, I will give everyone in the class an additional 3% on the final exam. So that's kind of a bonus for doing the survey. All right, so what else about the final exam? The time. It's really important. Okay? If you're in section 2, and that is the 1245 section, the final exam is 12:30 to 2:30 on Tuesday of finals week. If you're in section 3, which is the 11:10 a.m. section, 11:10 a.m. to 12:25, your exam is 10 a.m. to noon on Thursday. So make sure you know your exam time. Okay? You'll probably see that in the pre-lecture quiz. I'm just going to pull some easy questions from this little bit. The other thing to make sure that you know, this is in our normal classroom. Okay? And that shouldn't surprise you, although for Chem 151, we do all the finals at the same time, so you might have been in a different classroom for your Chem 151 final. Chem 152, we do not do that, so you're in your normal classroom for the final exam. All right, maybe one more thing. Final exam, we'll talk a little bit more about this on Thursday if you have any questions. Final exam will be multiple choice. Right now, there's only 2 professors teaching Chem 152 this semester. We do give a common final. Right now, we're at 47 questions on that. Okay, not a very round number, but that's where the exam sits right now. And I'm not sure I want to go back in and try to add more to it. So 47 questions. The exam does count 20% of your overall grade, so it will be very important for a lot of you. Okay? All right. I'm trying to think. I probably feel that I'm missing something about the final. You do have 2 hours, obviously, to take the final, so 47 questions. You should have enough time. I think that's about it. If you have any questions about the final exam, we'll start with that in class on Thursday. Okay? And then we'll then wrap up the semester with material. All right, enough of that. Let's get to the exam review. All right, so question 13. Okay, again, the first video of 1 through 12 is already done. The Ka values are indicative. These are representing just some generic acids. Remember, the common way to represent a generic acid is HA. Okay, there's the H plus, and then the conjugate base would be A minus. But we could also call a generic acid HB, HC, or HD. The Ka value should have told you that those were acids. So the Ka value is indicative of how strong the acid is. The larger the Ka, the stronger the acid. So this one, with 10 to the negative third, is the strongest acid. Again, it's all relative. These are all weak acids, pretty small Kas, but that's the strongest of the group. The one with the smallest Ka is going to be our weakest acid. So 10 to the negative 10th is our weakest acid. All right. So now question 13 was getting at the relation between acid strength and the strength of the conjugate base. All of these salts here contain the conjugate base. NaA contains A minus. NaB contains B minus. It also contains sodium ion, but that's not important to this problem. It also contains C minus and D minus. Those are the conjugate bases of those acids. So, the stronger the acid, what can you say about the conjugate base? Yeah, the weaker the conjugate base. So we want the strongest conjugate base, the most basic. So we want the strongest conjugate base. So the weaker the acid, okay, the stronger its conjugate base. Okay, and that T kind of disappeared. All right, so the weaker the acid, the stronger its conjugate base. So HA is the weakest acid, hence, and let me get this circle out of the way, A minus will be the strongest conjugate base and make the most basic solution. The weaker the acid, the stronger the conjugate base. Important concept. Oops, I'm sorry. All right, next question. 14. So this refers to the same ones. Which would be best to prepare a buffer of 6.8? Now remember, and we've talked about this throughout this exam, and you saw this earlier in the previous video, pH is equal to pKa is an important thing to know about the buffer if the components of the buffer are equal. Remember, your buffer has both a weak acid and a weak base that are conjugate pair. If those two concentrations are equal, the pH of the buffer equals the pKa. So a buffer works best centered around a pH that's equal to its pKa value. So for our choices, note HB has a Ka of 10 to the negative 7th. So if I take the negative log of that, so HB has a Ka of 1 times 10 to the negative 7th. If I take the pKa, the negative log of that, I'm going to get 7. Okay? So that would tell me a buffer that contains HB and its conjugate base, B minus, would be most effective at pH 7. And that's the closest to pH 6.8. So that's our best choice. Now there will be a range. Typically it's said, that it works, over a pH range of plus or minus 1. So this buffer, again, this is a fake buffer, but assuming it was a real buffer, you'd say it would work pretty well between pH 6 and pH 8. But it would work best, centered on pH 7. Okay, so the correct answer here is HB with its conjugate base B minus. If you look at the other ones, I tried to give you easy numbers on this. pKa of HA would be 10. pKa of HC would be 4, pKa of HD would be 3. So those would be the pHs at which those would be best as buffers, assuming you had the conjugate base with it. All right, problem 15. You should look at this and say, oh, it looks like a titration to me, right? Well, yeah, it says titration. But you see strong acid, you see strong base. So this is a strong acid, strong base titration. First one's really easy. We're starting with, in our Erlenmeyer flask, and that is a beautiful Erlenmeyer, we are starting with 0.2 molar nitric. And that's a strong acid. Okay, so what's the pH before we've added any base? So it's just asking what's the pH of that strong acid. So it's a strong acid, so what do you know about hydronium for a strong acid? Yeah, it's going to equal the initial concentration. So hydronium is 0.2 molar, pH of that, and where is my calculator? I always do this in recordings. I found it pretty quickly. How about that? Should be 0.7, yeah. Okay? So don't miss ones like that. That's just strong acid. Hydronium directly from the acid concentration, get the pH. Now, we're going to start adding from our burette. Okay, so here's our burette, which contains 0.5 molar NaOH. We are going to start adding that. Okay? And we're going to add, for this problem, 50 milliliters of sodium hydroxide. What's the new pH? Now, in any type of problem where the volume is changing, it's best to work with moles. I can get my computer to be happy here. So let's write out the reaction first, and then let's work with moles. So we have strong acid, HNO3. We have strong base, sodium hydroxide. H plus from the acid will be gained by hydroxide from the base, so it's H plus and OH minus. That's the main reaction. We will produce water, neutralization. We also get a salt in the process, sodium nitrate. All right, let's go ahead and work with moles. So don't forget, molarity times liters will give you moles. That's just rearranging the molarity equation. So our initial moles of nitric, 0.1 liter, 100 milliliters, 0.1 liter, times 0.2 molar. So that should give us 0.02 moles. 0.1 liter times 0.2 molar. Okay, now the base. 50 milliliters is 0.05 liters times 0.5 molar for the base. I get 0.025 moles. How much reacts? Yeah, all of it, right? This is strong acid, strong base. The base is going to grab every hydrogen ion it can. The acid is going to give it up. It's going to give up the hydrogen ion. It's going to give every hydrogen ion it has. So this goes to completion. But we have a limiting reagent. Which one is a limiting? Yeah, the acid in this case. So we're actually already past the equivalence point of this titration. Okay, 1-to-1 mole ratio, same amount of the base will react. We will produce product, but that salt is not going to impact the pH. And after this reaction is complete, strong acid is gone, and we still have 0.005 moles of strong base. All right. What do we do now? Well, we have strong base, so all we have to do is calculate the pH of a strong base, but we do need molarity to do that, not moles. So our total volume is what? What did we start with? 100 mils of acid. We added 50 mils of base. So now we have 150 milliliters total. Divide that by 1,000. .15 liters. That gives 0.0333 molar. Now, that's the concentration of sodium hydroxide, but what do you know about a strong base? Yeah, it dissociates completely into ions, so that will also be the hydroxide concentration. Okay, I said calculation, concentration. Take the negative log of that. That will give you the POH, because that's a negative log of hydroxide. POH is 1.48. Don't fall for choice B, which was 1.48. Subtract that from 14 to get the pH. And the pH is 12.52. Okay? Now, stop for 10 seconds and look at that answer and say, does it make sense? All we have in solution at this point that's going to affect the pH is strong base. So it better be pretty basic. All right? The salt's not going to affect the pH. We do have salt water, salt dissolved in water as well. But that's not going to affect the pH. So all we have is strong base. It should be pretty basic. So right away, B and C are out. Those are pretty acidic. So you could narrow it down, but it's going to be A, D, or E. The correct answer is D. All right, last part of this problem. A lot of times you will use an indicator to determine the equivalence point. Now, where the indicator changes color is actually the end point. You need to choose the indicator properly so where it changes color, the end point, is really close to the equivalence point. So for this one, we need an indicator that's going to change color at what pH? Equivalence point. What is the equivalence point, pH, for strong acid, strong base? Yeah, pH is 7. Okay? That's not this pH we just calculated. That's not the equivalence point, 12.52. Strong acid, strong base. The salt does not change the pH at the equivalence point, so pH is 7. So we need an indicator that changes close to 7. All right? Now, just like a buffer, indicators contain a weak acid and the conjugate base. So the color change is going to be centered around its pKa value. Okay? So you can go through and calculate all of these. I will tell you that the one that's going to be closest is bromethymol blue. So if you take the pKa of 5 times 10 to the negative 8th, for this one you get a pKa of 7.30. So that one is going to change color very close to pH of 7. Now, just like buffers, there's a range. It's typically plus or minus 1. So this indicator will probably actually start changing color about 6.3. But that's okay. Strong acid, strong base titration, the curve is really steep. So the difference between pH 6.3 and pH 7 is really small. All right. So the correct answer would be bromethymol blue, would change closest to pH 7. All right, 18. I've got a lot of writing in this document from the last two, this last key and this key, so the program's now running really slowly, but we'll see if we make it through. All right, so acetic acid is titrated with potassium hydroxide. So this is another acid-base titration. Let's write out the reaction, shall we? H plus from the acid is donated to hydroxide from the base to produce good old H2O. That's the main reaction. But we also do get a salt. Potassium ion, the conjugate base anion. But I'm going to write these separate because they will dissociate. They won't be together. But this is our salt that's dissolved in water. So what do we have at the equivalence point in solution? Remember, at the equivalence point, we've added just the right amount of base, potassium hydroxide, to completely react with the acid, acetic acid. So at the equivalence point, there's no base, there's no acid. The equivalence point, we just have salt dissolved in water, salt water. So now you have to look at that salt. What's going to affect the pH? Does potassium ion affect the pH? No, alkali metal cations are not acids. what about, this is called the acetate ion. Does that affect the pH? Yeah, absolutely. Because, why? Conjugate base of a weak acid. So the weak acid is acetic acid, which we started with. That's the conjugate base of that weak acid. What is the conjugate base of a weak acid? Yeah, it's a weak base. So it will make the solution basic. So this question says, what species in solution, let me read it correctly. The pH at the equivalence point is determined by what species in solution? Okay? It's that conjugate base, which is the base. That's going to make the solution basic. It's going to react with water, just to let you know. So since that's a weak base, it's going to react with water to do what? Base is a hydrogen ion acceptor, will produce the conjugate acid, but more importantly, what do we produce? Yeah, bases produce hydroxide. So that weak base, when it grabs an H plus from water, okay, we're going to be when water loses an H plus, we'll be left with hydroxide. Okay, so bases produce hydroxide. All right, so I did more work than you probably have to if you're thinking about this problem. Oh, at the equivalence point, all I have is salt. Well, what will that salt look like? Okay, it's going to contain the conjugate base of that weak acid. That's what's going to determine our pH. All right. Moving right along, not too much to do. Another titration problem. The equivalence point is an important point of the titration. Let us do various calculations. In Chem 151 lab, you determine mass percent of an unknown by titration. Another common experiment would be determine the molar mass of an unknown acid by titration. So we want the molar mass of that acid, unknown, but it's diprotic, 2 hydrogens. But molar mass, to do that, to calculate that, we need grams of that acid, and we need moles of that acid. What do we know? We know grams. And if that's what you would know. In the lab, you would measure out a certain amount of that unknown acid. Now you're going to titrate that unknown acid with base. All right, so now in the burette, we're going to drip in some sodium hydroxide and see when the equivalence point is reached, maybe by using an indicator. And so we need to find moles of acid, but that's not given. So how are we going to get moles of acid? Yeah, we're going to get it from the base. So for the base, we have its molarity, we have its liters, we can get moles of that base. Okay, so molarity, I tried to choose an easy number here for you, 1 mole per liter, 1 molar. That, you're going to have to convert that to liters, so 0.02295 liters, which would give us 0.02295 moles of base, sodium hydroxide. Is that equal to moles of acid? No, not in this case. If it was 1 to 1, yes. Is it the mole ratio here 1 to 1? No, because it's diprotic and has 2 H pluses, we're going to need 2 hydroxides. So the mole ratio is 1 to 2. So it's always going to be 1 H plus for 1 hydroxide to produce water, H2O. Since this acid has 2 H pluses, we're going to need 2 hydroxides. So we're not quite done here. We're going to have to take that moles of base, and I'll write NaOH this time. We want moles of, this is acid, 1 mole of H2A, and I tried to be nice, as nice as I could. I wrote the balanced equation, 1 mole of acid for every 2 moles of base. Moles of sodium hydroxide cancel. Divide that by 2. You get a few more sig figs here. This is 0.01148 moles of that acid. Plug that back in up here for your molar mass. I'm sorry. I apologize. As this document gets a lot of writing in it, it really has a tough time because I think saves all of these as some type of picture, and it takes up a lot of memory. So 1.722 grams. We now know the moles, 0.01148 moles. Divide those, and I get right around 150, 150.1 grams per mole. Okay, which was choice B in this one. Okay, so again, be very comfortable taking molarity times liters to get moles. You do have to apply the mole ratio if you're getting to moles of something else, so be careful. A lot of titrations will be 1-to-1, but not all of them, and this one is not. All right, last section of the exam, solubility. First question was designed to be pretty easy. Again, the magnitude of the equilibrium constant is really important. It will tell us the strength of an acid. It will tell us the strength of a base. It will tell us, do we have mostly product at equilibrium or mostly reactant? Now, these are insoluble, so these are all going to be small. Very little of those salts will dissolve. Okay? But again, the magnitude of that value will tell you how much. Okay? The larger the K, the more we go to product. Okay? The smaller the K, the less we go to product. And as these are written, these solubility expressions are the solid, so that should be equilibrium, dissolving in water to produce its component ions in solution. That's what that KSP represents. It represents the solid dissociating in water to ions. Now, none of these are going to dissociate very, very much. These lie very far, and I'm waving with my hand that you can see, obviously. These lie very far to the left. Okay? But, as I've written here, the smallest K, which is for tin 2 sulfide, means that one's going to lie the furthest to the left. Less of that compared to all the others will dissolve. So this one will have the lowest molar solubility, and I apologize. The largest KSP will have the greatest molar solubility. Now, none of these will be very large, but the one that will be most soluble in water is the one with the largest K value, which will be barium sulfate. All right? But we wanted the lowest. The correct answer on this exam was A, SNS, tin 2 sulfide. All right. Hope that helps. So know what the magnitude of K tells you. It's really important. You certainly will see that on the retest. All right. So, calculations, solubility. And it's saving my exam. I thought maybe it would speed up if I actually saved it. Don't know if that's going to be true. Probably not, but we are almost done. All right. Solubility of calcium fluoride in pure water. Okay? Now, calcium fluoride, all of these, you start with the solid in water. Okay, just like any salt, it's going to dissociate. Not very much, but a little bit will. Calcium is an alkaline earth metal, so you probably know. That'll be calcium 2+ in solution. But we're also going to get 2 fluoride, so don't forget this subscript of 2. Fluoride is -1, that's why we need 2 of those. All right, so let's set this up. Initial, solid's not going to enter into the equilibrium expression, don't worry about it. Water as a liquid won't enter. Pure water, those would be 0 to start. Not much of this salt will dissolve, but a little will. Let's call that X. Based on the mole ratio, we'll get X of calcium ions, 2X of fluoride. And at equilibrium, don't worry about the solid, X and 2X. KSP will equal to calcium ion times fluoride ion squared. So don't forget this coefficient of 2, you see it twice. You see it in the 2x, and you see it in the squared term. So our KSP value will equal to x times 2x squared, which is equal to 4x cubed. Don't forget to square the 2. 2 squared is 4. X squared times x is x cubed. Let's solve this. Divide the KSP by 4 and then take the cube root. And you will get, for your x, 3.32. No, that's weird. Did I punch something in wrong? I got 3.27. Hang on, let me just do this again. Maybe I punched something into my calculator wrong. Yeah, 3.32 times 10 to the negative 4th. Now, that is a choice. It's choice A on this exam. What is x, though? Yeah, this x is molar solubility. I don't know where all this other stuff just came from. I just noticed that. That's weird. That was not there before. Sorry about that. That hopefully didn't show up as the problem was going. It must be something I wrote somewhere else. X is the molar solubility. Make sure you know that. That's moles per liter. This problem asks for the solubility in grams per liter. So we have one more step. We have one more step. So this I might have to stop and save this and start over again. It's really running slow. That's in moles per liter. We want to get to grams per liter. So how do we get from moles to grams? Yeah, molar mass. Oh, I see what happened. My calcium kind of decided to go somewhere else. All right. So molar mass of calcium fluoride. Calcium is about 40. 40.01, I believe. Fluorine is 18. Now, fluorine is 19 times 2. So it's going to be right about 78. I might not get the exact answer. I don't have a periodic table in front of me. But it should be about 78 grams per mole. Moles will cancel, leaving us grams per liter. Get about 0.0259 grams per liter for the solubility in grams per liter. So a lot of times, if it just says solubility, a lot of times that means grams per liter. And that's a very common unit of solubility. How many grams of that salt will dissolve in a liter? Molar solubility is how many moles of the salt will dissolve. And that's what X is in that table. Remember, these square brackets mean molarity. And let's see, 0.0259, that was one of the choices, choice E in this case. All right, problem 2 is very similar to the preceding problem. I said problem 2. How about problem 22? It's very similar to problem 21, except we're not in pure water anymore. But the reaction is going to look the same. So I'm going to write it very quickly. Okay, initial, don't worry about the solid. Calcium is going to be 0, just like it is in pure water. But what about fluoride? Yeah, this is not pure water. This is a sodium fluoride solution. So that sodium fluoride solution is going to give fluoride, it's going to dissolve and put fluoride into solution. So that's going to give me, or us, or you, 0.01 molar fluoride at the start. So pure water doesn't have fluoride in it. So look back at the previous problem. These were both 0, but now we have fluoride at the start, still plus x and plus 2x because of the coefficient of 2. And at equilibrium, Don't worry about the solid. X, 0.01 plus 2x. All right. So note the difference between 21 and 22. Pure water, fluoride is 0. This is not pure water. It's sodium fluoride, which provides fluoride, or dissolves to have fluoride in solution. All right. KSP is still the same. Still calcium fluoride. X times 0.01 plus 2x. What else? Yeah, squared. Again, that coefficient of 2 shows up twice in the 2x and in the squared. Now, I know you really do want to solve a quadratic equation, but on the exam, you probably won't have time. So I know you would really like to do it, but on the exam, don't do it. All right. That was kind of supposed to be funny. Anyway, what do you know about the KSP value? It's really small. So very little of this salt is going to dissolve. So X is going to be really small. So we're going to make our small x approximation here. That 0.01 plus a really small number, 2x in this case, is going to stay about 0.01. So X is not 0, but it's really small. So we're hoping this number stays about the same, and it will. All right. So all we have to do to solve this is going to be 0.01 squared, and then divide the KSP by that. So I believe this comes out to 1.46 times 10 to the negative 6 molar. Again, X is molar solubility. So let me just double check. Yeah, so that's 1 times 10 to the negative 4th, 1 over X. Yes. Okay, that's our correct answer. Now this one did ask for molar solubility. So read the question carefully. Calculate the molar solubility. We just solved for that. 1.46 times 10 to the negative 6. All right. As you can see by my clock there, 5:46, I'm still at work. We're getting close. I'm getting hungry. I'm going to go home and get some dinner. Now, the previous problem, what we added, that fluoride that we added is, I like that did not circle. It's called a common ion. Okay? So fluoride was a common ion. How did it affect the solubility? Let's just go back and look at that really quickly, if it'll let me, before we do this problem. Because sometimes numbers are good to see. So let's go back up to pure water. Very slow. Molar solubility, 10 to the negative 4th, right here. Okay? Now we add a common ion. What happened to the solubility? So the common ion was fluoride. We have that in common. What do we now have for the solubility? 10 to the negative 6th. So it went from 10 to the negative 4th, and it decreased to 10 to the negative 6th. So just looking at those numbers between pure water and one with a common ion, adding a common ion decreases the molar solubility. It decreases the solubility of that salt. Okay? So this one just is asking you that in words. So we're looking at this solubility equation. We are going to add silver. So we're going to add this common ion. Okay? Now, based on the previous calculations, adding a common ion, you should already be thinking, oh yeah, it decreases the solubility. Why does it do that? Think of that French guy, Le Chatelier. What's going to happen if I add this common ion? If I add silver, which way is it going to shift? It's going to shift to remove some of that. Shifts to the left. Less of the solid is going to go to ions. Less of the solid is going to dissolve. So it decreases the solubility because it shifts it to the left. Okay, so if it shifts left, it goes to the solid. Less is going to go to ions dissolved in water. So adding a common ion, you might just want to remember this, is going to decrease the solubility. And it does that by shifting that equilibrium to the left. All right, last problem that was not a bonus question. This one's kind of hard. What we're looking at is calcium hydroxide. So we have to look at the solubility, because KSP applies to the solubility of that. So this is going to look just like all the other ones. Calcium 2+ in solution, 2 hydroxides in solution. Again, pretty small KSP. This does not dissolve very much. But what we're looking at is we're now going to mix a solution that contains calcium ions. We're going to mix a solution that contains hydroxide ions. And we're going to see if a precipitate forms. All right? Now, let me get a little bit more space here. The thing that makes this question a little bit harder is we are mixing the solution. So we are doing a dilution. So the calcium ions from the 300 milliliter solution are mixed with the hydroxide ions from the 200 milliliter solution. Both of those solutions are diluted. Before we do that, what we do need to calculate, just to remind you, is Q. Hydroxide squared. And compare that to the K to see which way this equilibrium will shift. So, to calculate Q, we need calcium ions, we need hydroxide. But we're going to dilute both of those. So we have to do 2 dilution calculations. Okay, M1V1, M2V2 for both calcium and hydroxide. So let's do calcium first. So calcium starts at 0.05 molar, 300 milliliters. We want its new molarity. It's now going to be 500 milliliters total solution volume, 300 plus 200. Okay, so calcium concentration initially is going to be 0.03 molar. All right, let's do the same calculation for, or a similar calculation for hydroxide. Hydroxide was also 0.05 molar. We only had 200 milliliters of that to start, and we're going to dilute that to 500 milliliters. So that one is going to be hydroxide. It'll be 0.02 molar. All right, so those are the concentrations that we need to plug in back up for Q. So let's recalculate Q, or let's calculate Q. I'm just going to write it down here. QSP, calcium, which is 0.03, hydroxide, which is 0.02, be careful, squared. So what is my Q value here? (1.2 times 10 to the negative fifth). All right, so in this exam, it has to be D or E, okay, because that's the Q value. So assuming we solve for that correctly, which we did, we've narrowed it down to that. Now, that doesn't tell us anything by itself. What do we have to compare it to? Yeah, we need to compare it to K. All right, so let's scroll back up here very quickly. If it will let me. 4.68 times 10 to the negative sixth. So, Q at 10 to the negative fifth is greater than K. Q is too large. We need to make Q smaller. Remember, at equilibrium, eventually the system's going to shift so that eventually Q will equal to K. So we're certainly not at equilibrium. It's going to shift one way or the other so that they will become equal. Q is too large. How do we make Q smaller? Yeah, we need to get rid of product. Remember, it's products over reactants. So to make Q smaller, we got to get rid of products. This is going to shift to the left. I'm sorry. I should have done this in two separate files. So let me draw an arrow. Shift left. Thank you. If it shifts left, what do we produce? Yeah, solid. We produce the precipitate. And so the correct answer, we knew it was either going to be D or E. It's not E. For this exam, it is D. Yes, we do get a precipitate because Q is greater than K. It's going to shift left, produce solid. If it goes the other way, if Q is less than K, if it goes the other way, it tells you they're going to stay as ions in solution and they're not going to precipitate. Okay? So the correct answer, because Q is greater than K, shifts left, produces solid. That's our precipitate. All right. That's the exam. I guess we can quickly look at 25. I think now that we've spent more time with electrochem, you're going to find 25 quite easy. So if there's a bonus question like this on the retest, you shouldn't miss it on the retest, assuming I can get to it. Okay. So remember, one thing will be a reduction. The other thing will be an oxidation. Here's the reaction shown for you. All right. So you just have to decide, looking at the reduction reactions, you have to figure out which one's reversed. Clearly, we have gold 3 plus going to gold. So this one looks like it stays as the reduction. This one is nickel 2 plus going to nickel. We have the opposite. We have nickel going to nickel 2 plus. So we have nickel solid going to nickel 2 plus. We don't need to balance this because it's already balanced, but there would be 2 electrons. So this is our oxidation. Okay? So what do you do to the sign of this reduction to make it an oxidation? Yeah, we just make that positive. Change the sign. So now we have a reduction potential. We have an oxidation potential. Don't multiply those. Those are all standard values, 1 molar concentration. If there's any gases, 1 atmosphere pressure. Just add those together to get the cell potential. And you should get a cell potential of positive 1.73 volts. Okay? All right, we made it. So again, the retest, Thursday night, 8 p.m., our normal classroom. Hope to see you there. Hope this exam key helps you as well. I know it just to go through and listen to this and write things down takes a lot of time, but it's really good because I've really tried as best as I can to explain these problems pretty thoroughly. All right, I will see you in class on Thursday, I hope, and I hope to see a lot of you at the retest. Take care.